All right. Hey, everybody. So in this video, this hopefully very short video, I want to introduce a new kind of notation which will be useful from time to time in the videos to follow. This is a notation that is commonly called Einstein summation notation, and it's a clever way to use indices to consolidate our notes and to make our summations, maybe complicated summations, look a little bit simpler. So I want to start with an example, something that we might compute at some point, or something that we have computed at some point in the semester. Simply a matrix multiplication of in this example, the first fundamental form with a given vector. So we have 4 entries, G11, G12, G21, and G22, and then we have our column vector here, right, V1 and V2. So this is our standard notation. We're using these indices. The first one represents the row that we are in. The second one represents the column we are in. And when I go to do the matrix multiplication here, I would end up with the expression G11V1 plus G12V2 in the top entry, and G21V1 plus G22V2 in the lower entry. And I could define these as top entry W1, bottom entry W2, giving me this equation for the top row and this equation for the bottom row. So we have seen, right, how we can write this out as a formula, and also how we can write this out in its matrix notation. But now let's take a look at this so-called Einstein summation notation, and that's as follows. So Einstein notation, in short, is a clever way to use indices, and in particular use both lower indices like subscripts and upper indices like superscripts in the same formula. So we take advantage of both upper and lower indices. And then the Einstein summation convention is that anytime we use the same letter as a superscript and a subscript, we will sum over that index, right? So we will sum over all paired upper and lower indices. In other words, if I had an equation with one variable, or I should say with one index, let's say a k, as a subscript, and in the same multiplication there's another index that's a k as a superscript, I would tacitly assume that I am summing over all possible k values. In this case, k would go from 1 to 2. So with that in mind, I could rewrite these formulas as follows. First, I could, instead of denoting my v's using my lower subscript v sub 1 and v sub 2, let me change those to superscripts. All right, and it's always worth remembering in this notation that the superscript is not an exponent, it is an index. So this is not v to the first power, this is v upper 1. And then this should be a 2, this should be a 1, this should be a 2. And so these two formulas can both be summarized in a single formula as follows. I could say that G1K times V upper K equals W1. And what we're seeing here is that as I sum over, since there's a lower script k here and an upper k here, that would mean that I would sum as k goes from 1 to 2. So that would be G11 V1 plus G12 V2. And I would take that summation to be sort of tacitly implied. And that would equal W1. Similarly, I could say that G2K times VK equals W2, and taken together, I could simply describe all of this using the very short formula GIK VK equals WI. Right? And so you notice that I started with two lower subscripts, right? A lower subscript I and k. I multiplied by this upper subscript k. Those k's sort of got canceled out in the sense that I summed over them, and the end result was an expression with just a single lower subscript, w sub I. And so this single line is really representing both of these equations simultaneously. This I could be either 1 or 2, and these two equations are implicitly using Einstein summation notation to describe everything that's going on up here. So you can see how you can use this notation to compactly write a larger summation that typically would come from maybe some sort of matrix multiplication or something like that. Let's see one more example of this. In fact, we've secretly already used or set up to use this notation, even though we didn't explicitly say it at the time. And this was when we looked at the differential of the Gauss map. So if you might recall, the Gauss map had a differential that had these aij's as coefficients. And even at the time, it was a little weird. We commented on it. The aij's used both superscripts and subscripts. So this was what we got. And this was the formula that we had, right? The second fundamental form, I should say negative second fundamental form, was equal to the first fundamental form times the Gauss map. And what we could see, or what we can see now, is that this matrix multiplication can now be succinctly written as follows. The ij entry of the second fundamental form, so Lij, rather negative Lij, would equal Gik times Akj, where here we're summing over our k's because of summation notation. Additionally, back when we were looking at this, we solved for the aij's by multiplying the left and right of this equation by the inverse of our first fundamental form. So we multiplied by the inverse of our Gij matrix, we moved that over to the other side, and we got a formula explicitly for our aij's. And that looked like this, right? So here, I am using upper scripts or superscripts for my G matrix to represent the inverse matrix. So sort of importantly here, we're saying that Gij as a matrix with superscripts is the inverse of our Gij lower scripts. That's our usual first fundamental form, right? So this is our first fundamental form. This is the inverse matrix of our first fundamental form. And what we're saying now is that if we multiply this over, we would get these superscripts. We would get this equation, which could be written using Einstein summation notation in this form down here. And once again, we're summing over these k's, and here the superscripts on our G mean that we're taking the inverse of our first fundamental form.